Okay, we're back. What's going on here? Well, remember that this matrix actually represented a very specific kind of transformation when applied to a vector. If you look at this matrix and you apply it to a vector, and what happens? The first component is left alone. The second component you add the first component to. And the third component you subtract 2 times the first component from. But how do you undo that? You undo that by subtracting the first component from the second component and by adding 2 times the first component from the last component. So with that we can guess that the inverse of this Gauss transform is given by this matrix right here, because that has the exact action of what we just talked through a second ago. And indeed, if you multiply these two matrices together, you get the identity. Now if you just compare and contrast these two matrices, what do you suppose is going on? Well, here you wanted to add the first row to the second row. Now we want to subtract the first row from the second row. Here we wanted to subtract 2 times the first row from the last row. Here we want to add 2 times the first row from the last row. And notice that all you need to do is reverse the sign that you have on your multipliers here to get to your inverse. That's summarized in the next homework that you just did. Here we have a Gauss transform. This here represents the vector of multipliers. And notice that to undo, all you need to do is negate those multipliers. So you can conjecture that this is the inverse of a Gauss transform. Of course, all of the sizes of these matrices need to properly match or it doesn't work. And indeed, if you multiply these two together, you again get the identity. Moving right along, let's talk about the inverse of a permutation, and in particular this permutation. So go and do some exercises about permutations, and then I'll see you in the next video.